I will try to give us a sort of common framework and some language to talk about different aspects of scientific research involving microscopic methods, and maybe suggest a few areas in which, well, I'll try to review the state of the art in a few different areas and suggest some places where new innovations might be beneficial. So I want to start with this framework from data to information to knowledge. So data is just what we measure off of our electron microscopy experiments, or any other experiments in this case. So because I'm an electron microscopist, I think about this in terms of electron scattering. So the data are fundamentally counts on a detector. How many electrons have hit which part of the detector. And we might measure them as a function of position in real space, position in reciprocal space, the sample orientation as a function of a set of angles, or the electron energy, or time. So we might have two-dimensional data, or 3, or 4, or 5. It's always important to have as many dimensions as possible. I'm sure there are people who are working on 6-dimensional microscopy of some kind, just for the buzz factor, if nothing else. But I'll certainly show you examples of 4 and 5D data over the course of the next 75 minutes. And this data is, of course, subject to noise, to distortion, to drift, to damage of the sample by the interaction with the electron beam, and by incompleteness. We often can't measure all of the data that we would like to have in a particular experiment. So then we'd like to make the step from that data to what I'm calling information. And this is some sort of abstract description of the important features that are in the data, or the information that those features convey to us about the sample. So this is a high-resolution STEM image. That's a 2-nanometer scale bar, so these are all atoms. So one abstract description of this kind of data is, where are all the atomic positions in this image, and how bright is each one of them, and how wide is each one of the atomic features in this kind of image. So I would say that's the information content in the few hundred kilobytes represented by the gray scales in this image. And ideally, we'd like to have an uncertainty in each one of those parameters. But of course, this is a pretty simple image. I think John has shown us that there is the potential for the information content in a data set to be the position of every atom in 3 dimensions with an idea of which element it is. And that approaches everything we might want to know about a piece of material, with the exception is we'd also like to know how they're all bonded together and how do they move. And that I would describe as the sort of ultimate piece of information about a system. We won't get all the way there every time, but we can get surprisingly close already using current methods. But that's really not the end of the chain, because usually what we want is some kind of knowledge, answers to our scientific questions, new insight into physical laws, or the quantitative determination of adjustable parameters in general descriptions of systems like the system that we're looking at. So for example, we heard from Angus earlier today and on Monday about defects in graphene, and they've got these beautiful movies of how they move, but the movies aren't the knowledge that you want. The knowledge is the formation and migration energy barriers for the different kinds of defects. The basic laws there are known, but the specifics for that system, the numerical value of those barriers, is the knowledge that we want out of that set of experiments. Now, of course, I'm not the first person to come up with this hierarchy. So Angus had pictures to numbers to properties as the subtitle of his talk on Monday. I think that maps pretty well. And in fact, in information science, they identify data to information to knowledge to wisdom. I am not going to pretend to wisdom. Oops, what have I done? I can't even run my computer, so I'm definitely not going to be wise. Now can I go forward? No. There we go. So no wisdom. I have none to offer. If we're good, we'll make it to knowledge, and that'll have to be it. So now I'd like to go through each one of these levels and suggest some things where we could do better and some areas where we're doing well, and maybe some opportunities where an intersection of mathematical methods, better experiments, and some prior knowledge might enable forward progress. So of course, we'd like to have better data. And often, our data are noise limited due to either damage to the specimen or because we'd like to gain time resolution to the point where we run out of signal. And Poisson noise in most of these experiments is unavoidable, but it may not be the only noise source. We'll come back to that in a little bit. And often in the experiments that we're doing, when we're talking about structures and objects at the sub-angstrom level, everything is always moving. The instrument is moving, the probe is moving, the sample is moving, the building is moving. We can't make it stop. And that results in distortion in scanned images and blurring in parallel acquired images. These are STEM and these are TEM images. And complicating efforts to improve the quality of the data is that the data is big and getting bigger. We're routinely acquiring single-digit gigabyte data sets in almost every electron microscope lab in the country. In my lab, we're now up to a couple hundred gigabytes for a typical experiment and a terabyte for a big one, and multi-terabyte data sets are coming pretty quickly. So there's a benefit to computational efficiency, both in terms of computing time and in terms of the scale of the hardware that's necessary to run a particular algorithm. Yeah?
And this blurring in STEM images, that does not exist in STEM images?
When you're talking about things moving, in the STEM, if you're sampling quickly compared to the characteristic time of the motion, the blurring will turn into distortion.
Well, that's because in STEM, scanning one pixel position is just maybe
is fast.
Very fast.
Yep.
And the STEM image acquisition takes a lot longer.
Yep. And so if you were to scan slowly, you can turn distortion back into blurring. And actually, Angus talked a little bit about this when he was talking about the need for high-speed detectors for his experiments. At 1 kilohertz acquisition, they've got blurring instead of distortion. At 10 kilohertz, they can get distortion instead of blurring. And I would argue distortion is better because in some ways it's easier to correct.
So is it possible just to ask, when you have the 10 images, and to correct them in your matrix there, is it possible to have a shutter and to make a lot of images one after another instead of just one?
You can make as many as you want, and the signal in each one of them will go down. Right? So there, you can run the camera faster and faster, and that will, again, reduce this blurring, but at the cost of introducing more noise.
What I'm asking is that that would be non-linear way of distorting, or this would be just linear, just kind of slicing information in several.
Let's come back to this. I've got some more slides about distortion later. Maybe they will help and we can try again. So I feel a bit embarrassed talking about noise after we have just heard from one of the world experts, but I'm going to do it anyway. And particularly because we were talking about extremely low count data, There are some specialized methods for just a few count mean, well not mean, just a few counts highest value, means of a tenth of a count or less, that can outperform some of the more general methods. We worked with Rebecca Willett, who developed this non-local PCA. It's described in this paper on arXiv, amongst others. And this is some very noisy data. I don't even have the original noisy data. It looks like nothing. Oh, the projector doesn't let you see the structure. Okay, you'll have to trust me that there is structure here in this image after the denoising, which is visible. And I should say, here's a very conventional non-local means, and here is BM3D, but this is without the variance stabilizing transform. So this is not really a fair comparison between, say, the non-local PCA and BM3D. But there are other forms. Peter, don't worry about it. I think it's just not going to come through on the projector. I don't want everybody to fall asleep because the lights are down. Turn the lights back up before they fall asleep. All right. There are other pieces of sort of prior knowledge about some of these experiments that we can also use to boost the denoising performance for particular problems. For example, lots of these atomically resolved experiments have an enormous amount of redundancy in the data. Every atom is more or less like every other atom. So we can take advantage of that. Here's an example of a non-local means method where Benjamin Burkles, who we're here from on Friday, and one of his students implemented a periodic search for similar patches inside the image to take advantage of the periodic structure in the data. And it substantially outperforms just a sort of blind similarity search, both in terms of speed, because you don't have to search every possible patch, and because the patches that you find are more similar. I was worried when we tried this that data that had an aperiodicity in the image, which is the part that I am most interested in most of the time, wouldn't denoise well, but it still works just fine. The aperiodicities are preserved even with the periodic search for similar blocks. And in a related piece of work, we worked with Arun Zhang and his student Rungang Hang in statistics at UW. They had developed a tensor SVD algorithm, which is effective and works for very large data sets, and applied it to one of these 4D STEM data sets. So 2 scan positions, 2 diffraction positions to make a 4-dimensional data set. But like this data, the spatial positions are highly redundant. There's a regular pattern because we're looking at a crystalline sample. And the tensor method for coming up with a low-rank representation of the data in order to remove the noise takes advantage of that redundancy in the way that non-tensor methods don't. So here's a comparison. This, I think, is simulated data, but the same thing works on experimental data with a noisy input. This is a real space image generated by averaging over the k-space coordinates, but here's a patch of the noisy k-space image. And here is the output PSNR as a function of the input PSNR for this synthetic data, denoised with a variety of different methods. We've got a non-local PCA, tensor SVD, a BM4D, again without the variance stabilizing transform, and then a conventional unwrap the whole data into a gigantic 2D matrix and use standard PCA, which actually is what people in the field are doing. We're 30 years behind the state of the art in algorithms, as per usual as experimentalists. And the tensor SVD is very good. It's not as good as the non-local PCA, but the reason that we denoised only this tiny patch is the full non-local PCA with the patchification of the data set wouldn't fit inside the available memory on our largest computer. And this little tiny problem took 800 seconds instead of 1 second. So the simple SVD is much more amenable to these very large data sizes and still takes into account or benefits from the redundancy that's inside the data set. The other thing that was interesting to me is the tensor SVD denoising actually corrects artifacts in the data that would otherwise occur in later analysis without the denoising. So here's an image, here's a sample image. It's a crystal. The crystal has fourfold rotational symmetry about all of the atomic positions. If we compute a map that gives us the indication of the degree of fourfold symmetry from the noisy data, we get a pattern that looks like this, but the correct pattern should look like this. Every one of these lattice sites has a fourfold point symmetry in 2 dimensions, and the denoising recovers the appropriate symmetry at every position, which is lost if we process the very noisy data. So the denoising really has practical consequences for this particular data set and measurement. Now people in the field are working on using deep learning to do denoising. Here's a fairly recent example from Peter Crozier. He's the microscopist, so he's the person I know, and Carlos Fernandez Granda, I think at NYU, who is the machine learning expert. The model and the other things are described here. They use simulated data in order to train a convolutional neural network. I think it's UNet. I'd have to look back to be sure. They made quite a large number of simulations, and on their data, the performance is exceptionally good. So we pulled this off the internet, and we thought, okay, well, we'll just try it. And we threw some of our images into it. This is not something that you should do. They're not the right kind of images. These are STEM instead of TEM. And for one of them, it worked really well, and for the other one, it didn't work at all. So I have asked a couple of times over the week about sort of guardrails on the use of these deep learning models. How do we know when they are likely to work and when they aren't? In this case, we didn't feed it very noisy data, so it was pretty clear when it completely failed to give us the right answer. But if these images were noisy enough that we really needed the denoising, then we would know whether the denoising had generated these kinds of artifacts or not. This makes me very nervous about all of these kinds of models because it's just so hard to know whether you're in scope or out of scope for the performance. So if there are evolving methods for determining whether something is in or out of scope for one of these deep learning models, and there's some ability to apply them to these kinds of problems, I think that would garner a lot of attention. Maybe not everybody is as nervous as I am, but you can also see right now, everybody who wants to do this trains their own network. And either that's because everybody else's networks are too hard to use, or it's because no one trusts anyone else's network because they don't understand the data that went into training it, and they're worried that they're going to get this. All of this is based on the idea of Poisson noise and artificially added Poisson noise to simulated data. It's worth talking, I think, just a little bit about how these detectors actually work and where the noise comes from, because it may or may not be perfectly Poisson distributed. So for the state-of-the-art detectors, these are direct electron detectors. There are 2 different fundamental technologies, MAP and PAD. They are, of course, both acronyms, neither one of which is particularly useful. MAP stands for Monolithic Active Pixel Detectors. The key feature of these is that the layer of silicon that transforms the energy from the incident electron into electron hole pairs that can then be detected by the electronics reading the sensor, this layer is thin. So most of the electrons just blast all the way through. They deposit some, but not all of their energy along the way. And because they are scattered inside the silicon, they don't just follow a single trajectory, they spread out. And the scattering process is random. So a random amount of energy is deposited in one or more pixels on the camera. They have the advantage that you can have a large number of very small pixels. The disadvantage that the way you make these images Poisson distributed is to apply a counting filter to the data after it's been read off the chip. And I'll talk a little bit more about what that means. And as a result, these have low dynamic range, meaning the map-based sensor that I have in my lab saturates at 12 electrons in a single pixel, and some of them saturate at 4. So they're good at measuring very low signals, and that's it. The other advantage they have is that they're very fast. The one in my lab, and there's one at Berkeley that run at nearly 100,000 frames per second. So they offer very high speeds. The other detector technology is pad. This uses a much thicker piece of silicon that's then bump bonded onto an ASIC that has a counter for every single pixel in hardware built in under the pixel. The reason that the pixels are big is they want to capture all the scattering from the electron and therefore all of the energy. So here is a bunch of simulated trajectory of 80 kilovolt electrons inside a pad pixel for one of the particular detector designs described here. You can see the boundaries of the pixel. All of the electron trajectories end inside the pixel, so they get all the energy from that electron every single time.
I think you just answered my question, but do you have backscatter that happens?
Yeah, some of the electrons will hit at the top and then leave. They can definitely head back the other direction. The cross-section for that is relatively small because the electron energies are high. So they've got a thick active layer. This distance is usually like 15 microns. This distance is usually like 350 microns. So it's a much chunkier piece of silicon. As a result, you get a much smaller number of very large pixels. And then the dynamic range is set by how fast you can count. So at a megavolt or a megahertz running the counting, you can get something like 1 million electrons before each one of the pixels saturates. But the speed is slower because you're running a whole bunch of electronics all at the same time. Another question in the back.
Yeah, it sounds like this is a problem that you have very large pixels, but can you not just have a bigger magnification before the electrons hit the detector?
Yeah, so you can adjust the magnification of the microscope over a very large range. But if you have a small number of pixels, and these detectors are routinely, 4K by 4K or even 8K by 8K arrays, these are more like 128 by 128 pixels.
Like you cannot make them larger.
So in fact, no, you can't. And the reason is, in the 1970s, Intel decided they never wanted CMOS chips larger than a certain physical size. So there are no silicon foundries in the world that will make single chips larger than the size Intel picked in the 70s. And since we don't have $10 billion to build a fab just to make semiconductors for electron microscope detectors, they are the size that they are, and we can't make them any bigger. There are plans to take chips and butt them together, and then you have to deal with the seams that are in between them. That's possible, but now the detector size scales, the detector price scales linearly with the area, which is also not great. Nope, you can ask your question here.
I just wanted to know what is, you say 100K
Yep.
On the same experiment, so that means you can revive it again, the left-hand side.
Yeah, so
You would have 100K detections per second.
yes, 100,000 images read out per second. Yep.
Okay, good.
And most of them will have almost no electrons in every pixel.
That's fine.
Yep.
So, about this price growing linearly with the area, but I would imagine that it's cheaper, according to this rule, to glue them together than going for a large one, at least due to the yield in the production.
I mean, they make the largest chips they're allowed to make.
Yeah.
And then if they want to make a larger sensor array, they have to mount multiple chips together.
Yeah, and if I'm aware of the problems that one encounters when you're stitching them together.
Right.
But if there were not those problems, I think that would be a very cost-effective way of getting a large detector, probably cheaper than manufacturing a larger one.
Ah, okay. Well, so these detectors have a huge number of pixels, not because the chips are larger, but because the pixels are smaller. And that means, to get one of these from the fab costs the same as to get one of these. Because the fab doesn't care how complicated your mask is, they care how long it takes to run it through the process. So if this chip is $100,000, this chip is also $100,000. So now, if you want a 1K by 1K version of this, you have to have 100 chips, and now it costs 100 times as much. So focusing on these map detectors for a second, because they are thin and because we don't collect all of the energy deposited by a particular electron is random. It follows this Landau distribution. So some of the electrons will deposit a lot of energy, some of them will deposit only a little bit of energy. And I don't know if it's visible from the audience, but here is an image of the distribution of single electron events on one of these cameras. Some of them are 1 pixel, like that one. Some of them are groups of pixels. Some of them are sort of lines and blobs of pixels, and that's because the electron trajectories are random. And the size distribution of events looks like this. For this particular camera, most of them are 1 or 2 pixels, which is good. Some of them are 13 pixels, that's bad. So to transform this into a counted image, we have to have a very low fill factor for the electrons to be detected, because if 2 of them overlap, then we have no way of knowing which one is which. Or whether it's 1 that's out here, or whether it's 2 that are down here. This process is pretty well established at this point, and it's one of the factors that limits the dynamic range of these detectors. However, as far as I know, people usually just run these things through a counting filter and then declare that the images are Poisson distributed, without paying a lot of attention to whether there are errors in the counting. The signal to noise ratio, the sort of peak here on my detector is about 110 counts, and the mean of this noise level is about 5 counts. So there's 20 to 1 and sometimes 30 or 40 to 1 signal to noise ratio for single electrons. So the errors in the counting are not particularly large, but they probably aren't 0 once you're counting millions or hundreds of millions of electrons. And I don't have any idea what that does to the distribution of the images measured in this way. And finally, you'll notice this value here is in analog to digital units, so these arbitrary detector units. And that means that they are subject to things like Fano noise in the primary electron to electron hole pair generation process, which add complexity to this distribution, add another source of noise to these, and I don't think that's been accounted for in any of these denoising models either. Okay, so I promised to talk about distortions. So here are two examples of distortions. Over here, actually, let me stop that. Where's my mouse? All right, stop it. So over here is a very high magnification image of a crystal. These are all gallium columns in a gallium nitride crystal. And you could see as the movie was playing that everything moves. The sample wiggles back and forth. And because the image is scanned from the top left to the bottom right, if there is motion of the sample or motion of the instrument, that turns into low frequency distortion of the positions of the atoms, not just into blurring. Beyond that, there's probe jitter, just high frequency motion of the probe. And then whenever the probe gets to end of one of these lines, it jumps back to the beginning, and that process isn't perfect. There's always some error in how far the probe jumps back. And here's a good example. This whole line of pixels here is shifted slightly to the left. That's a process that we call tearing, and it's because of this flyback error. So there are all sorts of distortions like this. In images that aren't acquired quite so quickly, like this one that I showed you earlier, let's track this layer of atoms from one side of the image to the other. So it's straight, and then it dips down a little bit, and then it goes back up, and now it's straight again. Only it's not. Planes of atoms are not allowed to bend for no reason. There's no physics there. Instead, what happened is probably somebody opened the door to the building, not the door to the microscope lab, and that was enough to make the sample move a tiny bit. And then when the door closed, the sample moved back, and that adds up to this kind of distortion in the image. So we've worked out a method with Benjamin again, with former graduate student Andrew Yankovich, that allows us to correct these kinds of distortions by applying a pixel by pixel registration to every single pixel in the image. And that lets us take images like this and turn them into images like that. This is a badly under-constrained optimization problem, so it required a lot of back and forth to sort of build in what we think we know about where these distortions come from into the algorithm that estimates all of the shifts of all of the pixels. And those are things like big distortions in space occur because they're slow in time, and as a result, they have to affect many pixels at once. Whereas very small magnitude distortions are fast in time, and therefore they can only affect a few pixels at a time. And those kinds of constraints enabled Benjamin to develop, and Peter, to develop a solution to this optimization problem. And that gives us, after averaging beautifully smooth, non-distorted images like this, where we can now measure the positions of these atoms to about 1% of the width of the images, which means very high stability, very low noise. And that gives us this sub-picometer precision in measuring the positions. This is all great. The problem is this data series is a dose of approximately 1 million electrons per square angstrom. If you think back to this morning, Angus was talking about 10, and like 20 was too high. So this is explicitly and exclusively a high dose technique. This is a very radiation-hard material. They make electronics out of it to shoot them into space so that the cosmic rays won't mess with them. We've tried it on other inorganic materials, and the acquisition will chew a hole in the sample before we get this level of detail. We can push the experimental methods to get down to a dose of about 10 to the 4 electrons per square angstrom, but that's still very high. And maybe there are methods where some additional prior information or some cleverness could be applied to do this kind of correction of the instabilities without requiring such high dose to be applied to the sample. Okay, so how much time have I taken up? All right, we'll have to maybe skip a little bit of stuff. The next thing I want to talk about is extracting information from these kinds of images. We've already seen examples from Angus of extracting atomic positions from high-resolution imaging, and from Angus and from John of extracting amplitude and phase from tychography or coherent diffractive imaging methods. I would classify all of those as ways to obtain information out of our data or 3D structure from tomography. I'll show you one example from our work of trying to obtain information directly from 4D STEM data without inversion like tychography. And then I'd like to spend a little more time on determining 3D atomic structures via optimization to solve inverse problems that we can't solve analytically. So 4D STEM by itself, the pattern of these disks and blobs that you've seen conveys all sorts of useful information about our samples. Sample thickness, crystallographic phase and orientation, the composition, whether there are internal electric or magnetic fields. And one of the ways that people extract this is to simulate a huge library of possible patterns using physics-based forward simulation models, and then do something like least squares matching between the experimental data and the library of simulations. It's the sort of most brute force possible way, I think, to solve this problem, but it did indeed work as shown here. So we thought, well, okay, if it works with least squares, maybe we can do a little better using a neural network to identify features instead of just brute force matching against a library. Question?
But how do you know that it actually worked with least squares matching? There could be several simulations that yield almost the same experimental images. Yeah,
I mean, that's true. In this particular case, because they understand the physics of the distortion that they're looking for, and they've picked a particular sample, and there's a sort of qualitative understanding of what the convergent beam diffraction pattern should look like, that's minimized. But in the general case, you're absolutely right. So we decided to look at the simplest possible property of a TEM sample, which is how thick it is. This is also a boring property. No one cares, but it makes a huge difference to the appearance of these convergent beam patterns, so we thought we would give it a go. We trained 2 different types of neural networks, a classification network and a recursion network, on a library of simulations, and then used them to match experimental data. And the matches are pretty good, and it does a good job ignoring things like rotations in the experiments with respect to the library. That's nice. And when it fails, that's because, to be honest, just by my human eye, I'm not really sure which one of these the experimental pattern really should match better. And it's because there's some noise and the data aren't perfect. So we did a variety of benchmarking experiments. These are the CNN determined thickness as a function of a different method for estimating the thickness. We'd like this to be a perfectly straight line. It mostly is. But as the thickness becomes large and the image features become more complicated, the models work less well. That's also a regime that's less interesting. We mostly want some thin samples. So this kind of worked. There was a lot of effort. It worked for one material. And then we tried to add what happens if we tilt the sample just a tiny bit. And everything broke. And it didn't work, and we couldn't train a network that would get us both the orientation and the thickness. So we hit a wall and decided, this stinks, we don't want to do it anymore. But maybe there's potential here for people who know more about neural networks than we do, or people who have the ability to simulate larger libraries of training data than we did. We had some modest success, declared victory, and moved on. So the other information determination problem I'd like to talk about is this idea of structure determination. Yeah, and that is, we've got some data, and we'd like to know where all the atoms are in 3 dimensions. One useful way, I think, to think about this problem is to place our samples on a sort of continuum from very well-ordered to completely disordered in the pattern of the arrangements of the atoms. And the reason that this is useful is it tells us something about the strength of our prior information about the structure. If we know that the structure is a crystal, and it has infinite translational symmetry, our prior information is incredibly strong, and that reduces the number of degrees of freedom that we need to determine to the number of atoms inside the unit cell. And that might be 5. For a really complicated crystal, it could be 1,000. Then we have all of the mathematical apparatus of crystallography to help us go from high-quality diffraction data, where we might have several hundred structure factor reflections experimentally, back to this small number of degrees of freedom we need to determine. If we add some disorder, for example, by making our crystal no longer infinite, but by introducing surfaces, and the surfaces don't have to be periodic anymore, in addition to being truncated, or by looking at a material that is a glass, still made up out of atoms. The atoms are still the same distance apart, but now there's no periodicity to speak of. The number of degrees of freedom goes up substantially, to the point where for n atoms in the glass, there are 3n degrees of freedom, and not a lot of additional constraints. And along with that, the data quality gets worse as the sample becomes more disordered. But we can still couch this as an inverse problem. We can, in general, calculate the experimental data from the structure, even when we can't invert to calculate the structure from the experiment. And the difficulty then is that the experimental data often does not uniquely constrain the structure. This is sort of like trying to solve a tomography problem from one projection. There's not enough data, you won't be able to do it. So you might think, why don't we add information about the energy of the system, right? Energy should be minimized. Generally true. At least free energy, a combination of energy and entropy, should be minimized. And there's lots of excellent work in the literature minimizing energy over structures using various kinds of search schemes to perform the minimization. Again, this works pretty well for crystals, where there's a small number of degrees of freedom. It works less well for more complicated materials with a larger number of degrees of freedom, and especially for real materials, kinetically trapped metastable structures are commonplace. If the global minimum in energy is here, the system very often might be here, or even trapped in one of these. The system will almost always be in a local minimum of the energy. It needs to be stable, at least to local perturbations, but it won't necessarily find the single global minimum of the free energy for that particular ensemble of atoms. And this is where it's very helpful to have some experimental data to try to tell you, is it this minimum, or this minimum, or this minimum on the high dimensional potential energy landscape. So one strategy to approaching this problem is to try to combine everything we think we know about a particular material into a multi-objective optimization. So we'll throw in an estimate of the system energy from theory, maybe some local data from TEM or from X-rays or X-ray spectroscopy, all sorts of other things. And then ask our magic global optimizer to find the right structure that obeys all of these constraints at once, plus maybe some other things that we know a priori about the sample, like none of the atoms should be overlapping. That's a very common additional constraint. Now, I can see those of you who know something about optimization are sort of looking at me like, sure, you've got your magic blue orb in the center of your slide. This is a terrible optimization problem. It's multi-objective, it's non-convex, very little is known about the object function structure. We're optimizing over thousands of degrees of freedom. So it's more of sort of a miracle that it works at all. But I'll show you two examples where it does more or less work and at least provides useful knowledge out the other side. And the last thing I want to point out about the nature of this problem, the theoretical methods for calculating the energy almost always give us all of the gradients of the energy as well at a minimal additional computational cost. And that can be used for local energy minimization via a simple conjugate gradient descent or something. Unfortunately, we typically don't have the derivatives of the experimental forward simulation, at least not without running the simulation a bunch of times, which is computationally prohibitive. So let me first tell you how we typically solve these kinds of experiments. We take beautiful images like this, we take beautiful spectra like these, and eventually we build models that look like this, but the way we do it is that the person who acquired the microscope images and I guess the structure. We hand it over to another postdoc who sticks it on the computer and runs density functional theory and tells us, no, not only is your model wrong, it is unstable. Not just the wrong metastable structure, but it is not even at a local minimum. And then we iterate a couple of times, and 18 months later, we've solved 3 of these fairly simple structures at the cost of $200,000. So this is the reason that we would like to do this computationally instead of the by hand method. So let me show you 2 computational examples. This is an image of a gold nanoparticle. It's a very slightly interesting gold particle because it has a defect plane going through the middle here. You look, the orientation of the lattice on this side is not the same as the orientation of the lattice on that side. We can estimate the energy for gold structures from a very fast, approximate method using an empirical potential. And we have this beautiful, smooth SEM image, which tells us how many atoms occupy each one of these columns. So we'll use an EAM potential for the energy. We'll use a STEM to constrain the particle morphology in the surfaces. We'll use a genetic algorithm as our optimizer for a multi-objective function with an arbitrary weight here that we might fine-tune a little bit by hand to try to make it work. And then hopefully we'll get out our solved structure. Because Peter brought this up earlier, one of the obstacles to this work is that the optimizations are going to require something like 1 million evaluations of the cost function, of the objective function. Quantum mechanical energies are too slow by a factor of 1 million. So empirical potentials for simple systems and ML-based empirical potentials may work for more complicated systems. That technology is coming along very quickly. But the STEM simulations are too slow by about a factor of 1,000 to be used in this kind of optimization. So instead, we used a very simple convolutional formalism, which is wrong but fast, and then a little bit of sort of patch up to account for some of the nonlinearities which are correctly captured by the multi-slice simulations. And it worked okay for a monatomic system. We've got only gold atoms. If we had any other flavors of atoms, this would not work. So we can...
question, Paul.
Yeah, sure.
What if there's a point defect? Can you figure that out? Or you assume it's perfectly crystal? And...
Not at this level. We wouldn't find it. The data are probably good enough to find it, but this ruins the potential to discern whether or not there's a point defect in the columns. It's not precise. The forward simulation from the STEM data is not precise enough. So here's the fitness function as it evolves over generations. And you can see that it drops consistently. And here's what our nanoparticle looks like in 3 dimensions. So it converged on something. It's reasonable. It's got the defect plane. In this movie, you can see it. There it goes, right there. And what was interesting to me about this result is these particles are made in solution. And as a result, everybody thinks they're spheres, or at least oval. And this one definitely isn't. It's pancake-shaped. And I think the reason for that is experimenter bias. We wanted one that was sat on the substrate in a way that gave us this beautiful view of all of the atomic columns. So my graduate student diligently found one with a flat bottom that was sitting flat on the support film that we used. So here's an example of bias in the data by selection by the experimenter, not by any other methods.
Paul?
Yeah.
Was this one that you initialized with a human guessed model?
Yeah, so we experimented with a variety of initializations for the structure. For some smaller test particles that we synthesized the data for, we could feed in random collections of gold atoms and it would find the right structure. This is about 6,000 atoms, so we cheated and we fed it FCC gold. So the only thing it's optimizing is the shape, the thickness, and the presence of the internal defect. We started it off with knowing the crystal structure for gold.
Okay. Still, it seems like it's discovered a lot.
Yeah. And I'm happy to show you. What's interesting to me about this reconstruction is it found some surface atoms which are blurred in the data because they move under the beam. But the data says, all right, there has to be an atom around here somewhere. And then the algorithm says, all right, its lowest energy position, its most likely spot is here. So in fact, we get a little extra information from adding the energy into the optimization that we don't get just from the experiments by themselves. Okay. All right, I'm not doing too badly on time. So the other example that I want to show you is a glass. These are materials that are made out of atoms, so they can't overlap with one another, and they have well-defined nearest neighbor distances and coordination numbers. There's 12 atoms surrounding each atom, or in the case of silica, like window glass, there are 4 atoms surrounding each atom. But beyond that, there's not a lot of extra structure. There's no long-range translational symmetry. So they have what we call short-range order, where each atom is a certain distance away from its neighbors because they can't get too close together. But it doesn't have long-range order. So what's interesting is what happens in between those two extremes. Maybe I'll take just 1 minute. This is one of my favorite figures out of any paper ever. This is a model of a metallic glass from 1964, before the days of the digital camera. They made the model by putting a bunch of ball bearings in a rubber sack, shaking it really hard, and then filling it with epoxy and letting it set. They cut the sack off, and these structures you see here are order imposed on the ball bearings by the hard sack surface. And then some poor graduate student had to take this thing and cut it into slices on a bandsaw and measure the center position of every one of the ball bearings in 3 dimensions in order to get the 3D model. But what's amazing is it worked they calculated experimental structure data from this model, and it was in a reasonably good agreement for experiments on a sodium liquid, which is a nearly hard sphere liquid. So I think John's method is maybe almost as much work, although much less mess, and you get a lot more detail. So our experiments, rather than trying to determine the position of every atom, we look at ensembles of atoms by doing nano diffraction experiments. This radius is about a nanometer, and then we get a diffraction pattern like this that depends on the structure of a few thousand atoms at a time. And that captures some of these second and third neighbor interactions and structure, which are the interesting length scale between the very shortest range where we know there's order and the very longest range where we know there's nothing. So in this case, we use the nano diffraction to constrain the nanoscale order, another one of these empirical potentials to constrain the energy, and we used a reverse Monte Carlo optimizer, not because it's the right one, but because it's easy to code, and we get a structure out the other side. I'm not going to describe what these data mean to you. I just want to point out that the open circles are the data and the red lines are the calculation from the model. The line goes through the points, so the optimization worked. The only other thing I want to point out is that this is a simulation of the experiment from a model where we minimized just the energy and didn't use the experimental constraint, and it's completely wrong. So, and this is a case where having the experimental data makes a huge difference in terms of getting a structure that really corresponds to the experiment. So we can dig through the model, we find two competing structure types, one of which has nearly six-fold rotational symmetry. That's crystallographically allowed, so this is sort of like a little crystal cluster that's trying to grow large enough to be thermodynamically stable but hasn't made it. And it competes with structures that are icosahedral. Those have five-fold rotational symmetry, which cannot tile space, so those favor the system to form a glass instead of forming a crystal as it cools. And we've shown in other work that the competition between these two structure types determines things like how fast can you cool the material from a liquid and still get a glass, how hard is it, what's the yield strength, stuff like that. Okay, so in the last 15 minutes, 13 minutes, I have only a little bit to say about this transition between information to knowledge. The first time I gave a talk like this, I said, "Oh, the machines aren't going to help us here. This is what the humans do." And I should have known, like every person who has said, "Oh, AI will never be able to fill in the blank," I was wrong. So I think that there are ways in which computational methods may be able to help us learn the general physical laws that govern materials, properties, and processes, including quantitative parameters, from microscopically resolved data. And I'll show you examples where we know the equations that underlie the system and we're looking for sets of parameters. But there are also examples where we would like to learn the relationships that govern the data, whether it's the right PDE or the right tensor property. And if you're interested in this area, I've put up here a couple of papers by Max Tegmark at MIT, who's been working on this kind of thing for a little while. Here's an example of a toy system that he was training a model to understand. These are trajectories of a particle propagating through a very strange space. And the upper left-hand corner, the trajectory is governed by a harmonic potential. Here, it's governed by nothing. It's just freely propagating. Here, it's governed by an electrostatic interaction. And here, it's governed by gravity in a particular direction. And he's trying to have the model learn all of these physical laws from many, many, many such trajectories, and also learn the boundary conditions and where the dividing lines are between those different kinds of structures. I'll talk about two kinds of examples. One of them is a very simple example, and it's one that I just drew on Angus's work here, but there are a number of people working on these kinds of things, where we can use high-resolution images to obtain data about the population of defects inside of a crystal and how those defects move from place to place and how they transform from one type of defect to another. Angus showed some descriptive examples where they used an AI model to go from this kind of data to this kind of information very efficiently and at scale. And then from there, the humans took over because we know the underlying equations that govern these kinds of behaviors. If the system is in thermal equilibrium, the concentration of different kinds of defects C depend on the concentration of monomers and some formation energy delta E. Now, we'd like to know what the delta E is, because that tells us what defects will happen at what temperature, how to form the material with defects that we want and not others that we don't by carefully trapping defect populations out of equilibrium. Knowing this number is very useful, even if we already know this general physical law. And the same thing for the diffusion, the motion of the defects through the lattice. It's also thermally activated, but knowing the activation energy is potentially a big deal. So Angus this morning said he boiled down 2 million images to 4 numbers. Maybe there's a way to have the algorithm just tell you what the numbers are, rather than have the human interact with the output result of those 2 million images. Even after they've been boiled down for their information using a neural network. But here's a much more complicated version of that same problem. And this comes from irradiation of materials, say, in a nuclear reactor. The incoming radiation continuously injects defects into the material. So there's a constant flux of new defects appearing all the time. Those defects then move through the crystal lattice, and when they encounter other defects, they might combine to make a cluster, and then the cluster can move, and it might split apart, or gain another cluster, or 2 clusters could come together and get bigger. And there's a mathematical formalism that describes all of this called cluster dynamics. The basic model is the evolution of the concentration of clusters of a certain size n is given by their production, the flux from smaller clusters, the flux to larger clusters, and the flux of clusters that leave the problem because they interact with a sink, say a surface where vacancies go and they just disappear off into the vacuum. Now these rates depend on an absorption rate and an emission rate. And n can range from 1 to 100, and that's for a monatomic crystal. If you have 2 kinds of elements in your crystal, say silicon carbide, now it's 1 to 100 for every possible combination of compositions for every size. So you can see you can easily generate hundreds of these equations with hundreds or even thousands of unknown model parameters in the most general possible cluster dynamics model for a material. This kind of model has been solved at full generality precisely once for tungsten, monatomic tungsten, and it took about 10 years. And no one is ever going to do it again, because it took forever and it's not worth the money. So instead, what people do is they fit some of these parameters, use like these absorption and emission rates using very expensive quantum mechanical calculations, and then they start making assumptions about what matters and what doesn't matter until they've thrown away enough of the parameters that they can get a tractable model, and then they run a bunch of simulations until they find something that fits the experimental data about the size distribution of the clusters as a function of time, temperature, and radiation flux. I got introduced to this because we made some measurements. You can't see it on the detector, on the camera here very well. Everything inside the red circle here is a defect, which we discovered using a new imaging mode. These are the red bars here. The blue bars are a model fit to the old data, which is wildly wrong in comparison to the new data. And then but with some adjustments and some changes in the parameters, they were able to fit the new data as well. And part of the insight that made that possible was we discovered that, are you gonna let me play the movie again? Yeah, the clusters move. And one of the underlying assumptions that had been made is once you've got something larger than a single point defect, it doesn't move through the lattice anymore. That turned out to be wrong experimentally. So there was a revision to the cluster dynamics model for this system. I feel like this is an example of an opportunity where the physical model is extremely complicated in its most general state, but what we really want is the minimal physical model. We want as many of these parameters to be zero as possible because they describe physics that doesn't happen. And we want to know what physics happens and what doesn't, in addition to turning out a quantitative model. And a system that could learn this kind of behavior and the parameters for something like a clustered dynamics model from data like this or data like this would be hugely powerful for this particular problem. All right, the last thing that I want to finish up with is an even more ambitious approach to these kinds of problems, which is being championed by Sergey Kalinin. Sergey will be here for workshop 2, I think? 4. Four, not until the end of not until the very end. But he will be here, so if you read his papers, he'll be excited and want to talk to you. He has this idea that there are systems where the physical laws or even the right structural descriptors are not known. There's enough disorder or enough complexity that we can't even write down the equations, or we can't even define the right features to go from data to the right information in order to get to the knowledge that we would like. And his scheme is to use machine learning to learn generative models from the data, models that can create synthetic data with the same statistical distributions as the experiment, which then means that somewhere buried inside that generative model are the features and the relationships that we would like in order to obtain the knowledge that we're after. I think that step is a bridge yet to be crossed. They're focused on developing the generative models, but maybe Sergey knows some things about this that I don't and can't tell you about. But this is the sort of, I think, the next big step in going from data to knowledge, mitigated by some machine learning along the way. Okay, I lied. I've got one more thing that I wanted to put in a plug for while I've got you all here. I'll be fast. We've heard a couple of times about the need for data and for training data for different kinds of models. The community knows that this is a problem, and we're working on the experimentalists are working on methods to try to solve it. And one of those methods is are data depositories, things like the Materials Data Facility. This is hosted by Argonne, funded by Department of Commerce and NIST. And it's essentially a giant pile of bits. People can upload whatever experimental data they like, as long as it's reasonably relevant, and MDF will give it a DOI and make it available. You can download it via Globus, authenticate with your home university credentials, and you're good to go. So if over the course of this workshop you're thinking, boy, I really wish I had an example of fill in the blank, it might be helpful to go to materialsdatafacility.org and use their search tools and see if you can find an open and accessible version of the data that you would like. Beyond that, I'm part of a collaborative team that's working on a system they're calling Foundry to take machine learning models and permanently associate them with their training data sets. The idea being that a model by itself, not particularly useful for some of the reasons we talked about earlier. Data by itself may be useful, but better if it comes with a model. So we want to make both of those things available and permanently associate them with one another. And then provide a Python API that allows you to access both of them without too much trouble. The Foundry data sets are easy to access and load. We've made some predefined, very general schema for common materials data types, including images, which require people to provide some level of appropriate metadata, and if they're using them to train a model, provide the splits into different training and test sites, or splits as a function of image quality parameters or something. So there's an example data set from my lab, which we put together for this atom finding problem. Let's try to locate all the atoms in high resolution images. If you want it, it's got simulations, it's got a bunch of experiments, it's got ground truth for all the images, and if you want it, there's the DOI. I won't leave it up long enough for you to copy down, but I'm happy to send it to you. And it's free. You can just go get it, download it, do whatever you want. Just please cite my paper and the DOI so that we get credit for the work that went into making it. And then on the model front, the system will do is take the models and put them inside containers so that they will continue to run even after version changes in the underlying libraries, which is a thing that at least drives me and my students completely crazy. You go to somebody's GitHub and you think, great, I've got the code. No, it's not going to run, right? This will run because it's sort of sealed in amber. And as long as the container continues to execute, which hopefully the container service, it's called FunkX, will make that continue to happen, it'll continue to work. Right now, it executes on hardware at Argonne. There's capability for executing on local hardware coming, but not ready for prime time yet. And it offers CPU-only execution, but you can try it out if you so desire. And did I put the DOI? Okay, sorry, I didn't put the DOI to any of the models up. I've got them, I'm happy to share them with you. Okay, so I hope this was helpful. You look like you're all still awake, thank you for that. We talked about the fact that we often follow a data to information to knowledge chain in, all of scientific research, but in research on microscopy and materials particularly. And I think there are opportunities for improvements all along the chain. We saw some examples both in this talk and in the previous talk that I won't go through entirely because I think I'm out of time. Thank you very much for your attention.